So recording started.
Okay. Welcome everyone. Today we will start from where we left off in our last lecture. So remember that we were talking about non-abelian gauge theories and some of the main formulas that we derived, and then we will move on from there. So the main thing that we discussed in our last lecture was how to construct the action of a theory that has a non-abelian gauge symmetry. So how to construct a non-abelian gauge theory. The first thing that we do is first we construct a classical non-abelian gauge theory. And so what that means is that is invariant under a non-abelian gauge transformation. And there are many ways that you can construct these kind of actions. Some of the simpler ways, and one that we discussed, was that you start with a theory that has a non-abelian global symmetry. So you start with an action with global G-symmetry. And in practice, G can be many different things, but the cases that we are interested in, G will be a compact Lie group. And in particular, so you can, for our purposes, you can take it to be UN. Okay. And so what it means to have an action with a global G-symmetry is that, so this action will have fields. So it will contain fields that will transform under various representations of your symmetry group. Fields and representations. And what were representations? They are homomorphisms from your group to invertible matrices. And so let's say that we label the components of vectors belonging to V with I. That goes from 1 to, so whatever the dimension of this representation is, or dimension of V. So we can call the dimension of V, or we can call the dimension of R. It's the same thing. And so then if you take an element X from your group, then this X will act on the fields of your theory. For example, you may have some fields, phi, which will have an index I, of course, because it is an element of this vector space. And it will transform into a new field, phi prime I, which is nothing but the action of on V. Something like this. And the invariance of the action under this transformation means that if you evaluate your action on phi, that's the same as evaluating it on the new field phi prime. Okay. And I'm writing phi as a stand-in for any field that transforms under some representation of this group. This can be boson or fermion. And the representation can be anything really. And also recall that associated to any such representation of the group, we shall also have a representation for the Lie algebra. From the Lie algebra of the group to all matrices acting on the same vector space. All matrices that act on V, not just invertible. Okay. So this is the data that you start with. This defines an action with a global symmetry given by G. And then in order to, the next step is that you promote this global symmetry to a local symmetry. So that step involves replacing all the partial derivatives with covariant derivatives. So replace del mu with del mu minus I. Here G is just a number, a coupling constant, and then presentation rho of A, where A is the new vector field that we introduce, which has to transform in a certain way. And also mean A mu rho of TA. Here, these TAs are our basis vector for the Lie algebra. So in particular, this index A goes from 1 ... dimension of the group. Okay. And the constraint on A is that when you transform your fields, you also have to transform A when you do a gauge transformation. And the transformation of A was a bit unorthodox. It goes to minus partial derivative of, so theta is a field. Well, theta is a parameter that depends on spacetime, and this is the parameter of your gauge transformations. Something like this. So here I am writing upper and lower indices to imply that there's a summation over these indices. But again, remember that for UN, which is going to be the main example that we discuss, there is no distinction between upper and lower index because you raise and lower index in UN with the Kronecker delta, so it's the same. Okay. So in practice, in your action, you will have derivatives of and just to remind you of the notation, when phi is vector valued, this simply means that you take a matrix of partial derivatives and then you act on the components of phi. So here for now, let me write dimension of V. Let's keep the representation generic for the moment. But if we're talking about the fundamental representation, then of course dimension of V is going to be n if we're talking about UN. So this is simply del mu phi 1 del mu phi dimension of V. Okay. So then when you promote partial derivatives to something like this, so here, this is how is this thing is a dim V times dim V matrix. And you will simply multiply this matrix with this vector, which will give you another vector. That's how this part acts on your fields. Um, the examples to keep in mind are, for example, you can have scalar fields. When I say scalar, I mean scalar with respect to spacetime, but you will have multiple components because it will be valued in some vector field V. And then the kinetic term for the scalar field, before you do the gauging, when you just have the global symmetry, it will be, so del mu square simply means del mu these two phi dagger, del mu minus IG. Phi. And if you have a fermionic field psi, then the kinetic term looks like this before you do the gauging, and then this is simply replaced by the same thing basically. Okay. So this is the modification for the kinetic terms. And remember that there are no modifications for the potential terms, assuming that those terms do not involve derivatives. So they are invariant by themselves. Okay. And then we said, well, okay, so this is simply a modification of the action. At the quantum level, we haven't introduced a gauge theory yet. We have simply coupled our classical theory to a background gauge field. So that's just the language that you use to describe what you have done so far. But then, in order to do the quantization of this gauge field, so first we have to add a kinetic term for the gauge field. Add a kinetic term, which is called the Yang-Mills term, and it looks like this is normalized in some way, so something like this. And so remember that this trace means F mu nu A, F mu nu A, where again A is the index for the Lie algebra, the same index. Okay. And of course, this F is the curvature tensor or field strength tensor. Right. So you add a kinetic term and then you do the integration over your gauge field. So basically the steps are as follows. You start with a theory defined by path integration that involves some fields. So here again, so phi is just a stand-in for whatever fields you have, some boson, some fermion, some other things if you have it. And then the first step is that you couple this to a background gauge field. So you modify the partial derivatives to covariant derivatives. So now you have an action that involves the fields that you originally had and the gauge field. And then the next step is you integrate over this gauge field after you add the Yang-Mills term. Okay, I'm running out of space. So this step is simply called, well, it can be called many things, but you can also call it coupling to a background gauge field. And this step is the quantization. You can also refer to as promoting the background gauge field to dynamical gauge field. Okay. And then we said that this idea is fine, except that there is a lot of redundancy in this integration over these gauge fields. Actually, it's not just in the integration, also the integration over all of the fields because of the gauge symmetry. And we discussed some finite dimensional analogy where you are basically trying to do an integration over two kinds of variables, whereas the integrand only depends on one of the variables. So this entire integration over dy is redundant, and this gives a divergent factor. Similarly, because this part is invariant under a gauge transformation, so all of the fields in the orbit of gauge transformation give you the same value. So we can basically treat this integrand as independent of the coordinates that parameterize the gauge orbits. And therefore, if you separate this integration into an integration along orbits and integration transverse to orbits, then the integration along the orbits give you a huge divergent factors to systematically get rid of the divergent factors. So that's going to be the main thing that we discuss now. So before we start discussing that, so this was basically a quick recap of what we discussed in the last lecture. So is everything clear so far, or are there any questions?
Very clear, thank you.
Okay, good. So if there are no questions, then let's try to discuss how to make sense of this integration when there's a large redundancy. All right. So let's stick with this finite dimensional example first. Let's try to understand how we would tackle the problem of integration over dy in this case, and then we will mimic that into the infinite dimensional case. Okay, so let's start with this. And here is that we are trying to do a two-dimensional integration. But our function depends on only one variables. So really, we don't need to do a two-dimensional integration. We just need to integrate over x. So you could just say, all right, so drop this integration variable y altogether. Why do we need it? That is a valid question. Except in this case, the separation into x and y is not super obvious. I mean, we know in principle what we have to do. We know that we should separate the fields into gauge non-equivalent parts and the fields that are gauge equivalent. But obviously, that's more non-trivial to do here than it is here. Here, I mean, obviously, we can see that there's no y dependence here. Here, less obvious. So let's try to be more systematic. So what is going on? I mean, we are trying to make some analogy with the infinite dimensional case, right? So what's going on in the finite dimensional case is that so here we can say that translation in the y direction is a gauge transformation. So at any point x, we can translate in our integration domain, right? So we get these vertical lines, right? These are the translation lines for the y direction. And our integrand does not depend on where we are on these lines because it doesn't depend on y. So that's the analogy with this case, that given any fields, we can move in the direction of gauge transformations. So we can get to other fields that are related by gauge transformation. So here, starting from any point, we can go to any other point that's related by a vertical translation. And so these are the things that we are trying to get rid of. We don't want to integrate over these vertical directions. So we can say, point is that, so our physical intuition is that all fields that are related by gauge transformations are equivalent. We should not distinguish between those fields. And that's why it doesn't quite make sense to say that just pick this x-axis. Because there is, I mean, in a strict sense, there is no distinguished x-axis. Any point on this line is the same as any other point on this line. So there is nothing special about this point. Okay. So what I'm trying to say is that we should be able to pick any line like this that goes through these vertical lines transversally, meaning that it doesn't intersect the same vertical line twice. And then the integration over this line should be this line or integration over this line or any other such line. Right? So that's a physically meaningful thing to say. And that's what we want to implement. That instead of integrating over an entire orbit, we will pick a particular point from each orbit, and the final result will not depend on which points we chose. Okay. All right. So let's say that we want to do an integration over this line. So what is a line in 3D plane? A line in a 2D plane is simply a solution to an equation involving both variables, right? So choose whatever function f you want. Just make sure that the solution to this thing, which is a line, doesn't intersect the vertical lines more than once. Okay. And let's say that we want to integration. We want to do an integration over this line. Okay. So what can we do? So the most obvious choice is that maybe we can insert a delta function here, a delta function that is only non-zero on this line and zero everywhere else. So then obviously this integration will localize to the line, right? So let's try to do that. So insert a delta function that is supported on the zeros of this line. Okay. Okay, so this is a modification. I mean, this integration is not equal to this integration, right? Our logic is that we shouldn't have started with this integration at all. Rather, this is the kind of things that we want to do. But let's check what we get by doing this integration. Okay, so careful. So we said that if such a function that f of xy equals to 0 gives you this line. But if you are not very careful about picking your function, you may end up with a function that has multiple solutions when you solve for y, meaning that this is some equation that you're solving. And suppose that if you're solving this equation for y, that you may get multiple solutions. So maybe y is something like this, y1 of x, or y2 of x. There can be a bunch of solutions, actually. Let's say yk of x. Maybe there are k solutions to this equation. And if you're getting confused, so what I mean is that suppose as f of xy, we chose something like the following. Y squared plus x times y, and then some other arbitrary function of x, right? Let's say that this is our f of x, y. Then if you set this to 0, this is quadratic in y, right? So obviously we'll get two solutions. There'll be y1 of x, and there'll be y2 of x. And you can write down explicitly what these things are using the formula for solving quadratic equations. So this is what I mean. So if that is the case, actually, so what would something like this mean here? I mean, this line that we drew, obviously for any point, any value of x, there is a single value of y. So what's going on here? So if you have k solutions, then for any value of x, you have k different values of y, right? So actually what's going on here is that if you pick fxy, which is, say, degree k in y, then you will have this situation. And then if you look at the zeros of this function, you will find not just one line, but you will find k different lines. we'll find something like this. Okay. So that how many lines should I draw? 1, 2, 3, 4. Okay, so this will happen if f is quartic in y, and then for any value of x, you will find 4 different values of y where this function vanishes. This is not exactly what we want. I mean, this will not be the end of the world, but because it's still a finite degeneracy, so you can divide by whatever you got. But anyway, that's not the ideal situation. Okay. So you can functions. Maybe some functions are very easy to deal with, but it gives you a multi-sheeted cover. And then you have to deal with that multi-sheet. Anyway. Let us remember a general formula. So for an arbitrary function f of x and y, if we evaluate this integration, meaning that we are trying to do the integration over dy using this delta function. So what do we get? So you get a sum over all solutions of this equation. And then you're left with an integration over x. Obviously, nothing happens to f of x. And then from each 0, you get a factor like the following. So derivative of del f with respect evaluated at solution, derivative with respect to y, modulus, right? Okay. Maybe you remember this formula. If not, well, okay, you can look it up. It's easy to prove. Just expand your delta function around each solution. Okay, so this is an improvement in the sense that here we had a divergent integration. Here, our integrand only depends on x. Just to be clear, yj is a function of x. Right. Okay. So this part depends only on x. This part depends only on x. This is an integration over x. Seems okay, right? But there is still one problem remaining with this expression. I mean, other than the fact that, again, as I said, that you can be clever with your choice of function so that it only has one solution, in which case k will be 1 and there will be no sum, just that one solution. So that's fine. That's not the problem. There's a slightly bigger problem, which is that the integral should not depend on f. Okay. And this was the gauge principle, that all of these fields on the same line were completely equivalent. I mean, okay, in this case, there are no fields. Everything is, we're working with zero-dimensional spacetime. But the modification to this integration that we're trying to do at the end of the day should not depend on our choice of this line. Maybe you get this line for some choice of f, and you get this line for a different choice of f. They should still give you the same integration if our principle is correct, that every point on this line should be treated as completely equivalent, and similarly on any vertical line. That is not happening here, right? Because this part explicitly depends on our choice of f. So how do we remedy that? Well, instead of inserting just this delta function, we could have inserted a bit more. We could have inserted something else that would cancel this extra factor. So what is that extra factor? So we could have done the following: dx dy delta f. Take this thing, right? Also, for simplicity, let us assume that we choose f in a way that this derivative is always positive, so then we don't have to keep writing these absolute values. just insert this function. Not evaluated at any specific values. Just take the function f of x and y and just take its derivative and put it inside your integration. Okay. And then what do you have? So now if you do the integration over d of y, so what will happen? Because of this delta function, you will produce a factor like this. And of course, now you will substitute the value of y, right? Because delta function will pick those specific values. So then this will cancel exactly this factor. Dx f of x. Okay. So we ended up with the expression that we really wanted, right? That just forget about this dy. Why do we need it? So that is what we ended up with. But now we have achieved it in a way that is directly applicable to this situation, even when we don't have a clear separation or an obvious separation of variables into longitudinal and transverse directions, okay? Which is what we will discover now. All right, and this is basically gauge fixing. So you have to choose some function that picks one point from the gauge orbit, and you do that by inserting the delta function. Then you have to insert something else using a particular function, okay? So these are the two steps involved in gauge fixing. Choose a gauge. So this is the choice of gauge. And this is called defining a gauge invariant measure. Okay. So let's implement this in gauge theory. Well, actually, okay. Let's go through an intermediate step. Let's first implement this in a multivariable case. I mean, it's still in 0 dimension, but multivariable, which is straightforward to do. So what I mean by that is that multivariate. So again, reason you started with an integration as follows. And here by f of x, I mean f of x1, x2, xm. Okay. So now there are n variables y that doesn't enter into your integrand. And these are the things that you want to get rid of. So what do you do? This generalizes in a straightforward way. Let's see. So notice that this part, let's see. This is the kind of factors that you get when you do a coordinate transformation. Give you df. Okay. So remember from your calculus class that you have dy and then derivative of something, partial derivative of something with respect to y. This simply changes the integration variable from y to whatever this thing is. So basically, you are changing variables. You have x and y, and then you are changing these to x and f. The reason that it's useful is that if f is your independent variable, then this delta function is simply delta f, right? So it's just a single variable, and you're picking up the value over integrand at the 0 of that variable. And this completely gets rid of any ambiguity that might. Now you just have a variable called f, right? It doesn't matter how f originally depended on x and y. Whatever that choice was, f is now just an independent variable, and you have a delta function that simply kills that variable. So that's why you basically get a function independent result at the end. So we are going to mimic that situation here. The first note that you want to kill off n variables, right? There are n variables y1 dot 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 yn that do not enter your integrand. So in order to kill off n variables, you need n constraints, right? Each constraint will kill off one variable. So now you have to choose n functions. Choose. So now you have f1 xy dot 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 fn xy. And we want to set all of these to 0. And they're all set to 0. So those are our constraints. Now, similar to what was going on here, we want to trade off these variables y for new variables f1 to fn. So we simply accomplish that by inserting the Jacobian, or the determinant of the Jacobian. So you have the determinant of this thing. And okay, if you remember the norms, you have norm of the determinant. But again, in practice, we will assume that our choice of f is such that these things are positive, because it is difficult to deal with absolute values analytically. Okay, then the delta functions. So you need one delta function for each constraint. So delta f1, delta fn. We can also just write it as the same thing. And then what we had before, f of x. Okay. So again, the purpose of this group is simply to replace the variable y with the variables f. And then these delta functions are simply telling you that pick the value 0 for each of these variables. These variables do not appear here, so you don't have to do anything. This is simply dmx fx. Okay, great. Just to clarify my notation. So when I say that determinant of this thing, I mean that there is a matrix. There is a matrix like this. This is a matrix, the Jacobian matrix. And so take the determinant of this matrix. That's what this means. Okay. All right. Again, as you can observe, that the final answer is obviously what we want. And in this case, we could have gotten to this answer simply by eliminating this power. The reason that we are going through these intermediate steps is that these are the things that we can mimic in the field theory setting. Not exactly this. Again, because we don't have a super clear separation between transverse and longitudinal variables in case of QFT. Okay. So now, okay, again, before jumping into the QFT case, let's try to do some more mimicry. In particular, determinant. Remember from probably your assignments the following formula. So if you have n fermions or n Grassmann variables, let's call them C, Ci and C bar I, where I goes from 1 to n. Then you have the following formula. You can do a Gaussian integration for these Grassmann variables. So dnc, dn C bar, integration of e to the power minus I. And then here, any matrix, any n by n matrix. This is up to some factors of 2 pi and whatnot. Simply the determinant of this matrix. Okay. Here it's any. We will take it to be non-degenerate. Otherwise, you would get 0. Non-degenerate n by n matrix. Okay. So this is a very useful formula. This formula allows you to convert the determinant of any matrix into a path integration. I mean, here, of course, we are doing the 0-dimensional activity, so we are doing just a finite number of Grassmann variables. But the idea persists. You can convert the determinant of an operator, in this case a matrix, into an integration over Grassmann variables, a Gaussian type integration for these Grassmann variables. Okay. So using this trick, you can convert this determinant into something more field theoretic, right? So what you can do is that, okay, I'll write here. So this determinant, and this may get a bit confusing. I'll write it somewhere else. This determinant is an integration over Grassmann variables like this. Okay. Okay. So what we have done is that we have introduced some new set of fermionic variables that allow us to convert this determinant into a Gaussian integration. Okay. And you can imagine why this might be useful, because in practice, when we want to apply this to gauge theory, the integrand that we have in mind is the exponent of the actions of the things. So this f will be the exponent of the action type thing. And now this determinant also looks like e to the power c cc bar type thing, right? And some Gaussian. So it also looks like some fermionic action type thing.
Is this only applicable to fermions, or do they apply to bosons also? This determinant, the identity.
This identity?
No, the one on top of it. Yeah, that one. Both are the same.
Yeah, they're the same. No. Here, these things have to be fermions, because if you replace these fermions with bosons, then you don't get determinant of M. You get the determinant of M inverse. Right?
Okay. So it's a different identity for the bosonic case. Okay.
Yeah, it's only, I mean, the only difference is that in the bosonic case, you have an inverse.
All right. Thank you.
Now, so you can apply the bosonic identity as well. So if you can show that, well, okay, so this determinant is going to be a determinant of some Jacobian, right? Which is the inverse of the determinant of the inverse Jacobian. So you can use the inverse Jacobian, and then you can use some bosonic variables, which may be, okay, so there are examples where you have to do that, but that's not the first thing that you do, or that it's not the first thing that you would try. because on the nose you have a determinant of something, which is given by a fermionic Gaussian integration. So that's the straightforward thing to do. Okay.
Okay, thanks.
Yeah, not a problem. So now we will try to generalize this to the infinite dimensional case. Any questions so far? In chat? No. Okay. Yeah. So please ask any question if anything is unclear, because sometimes some notations are maybe they have not been introduced before, and there's no point in getting stuck due to notations, right? So make sure that all of the notations are at least clear. Okay. Now, before we move on and implement this in the infinite dimensional case, we need to take a brief detour to discuss some representation theoretic aspects. Detour on adjoint representations. Yeah, I think you had some lectures on representation theory at the beginning. You discussed adjoint representation, is that correct?
I don't recall.
Okay, well, we need some basic formulas, so maybe we can briefly recap some of the basic formulas. Okay. But if I'm going over things that you have already seen many times, then maybe we don't need to do that. So there's a question in chat. So why we need Grassmann calculus of variables? What is Grassmann physical meaning? So there is not going to be a very satisfying. Okay, let me repeat the question. So the question is why we need Grassmann calculus or variables, and what is the physical meaning of Grassmann variables, I think. Okay, yeah. So as I was saying, there is not going to be a very satisfactory answer to that question, because at the moment, the only answer is that in field theory, when we have something inserted inside the path integration, it is technically convenient to be able to interpret this thing as a modification to the action instead of treating this as the insertion of a non-trivial operator. Okay. I will not elaborate on this too much right now, because when we finish discussing the implementation of this thing in quantum field theory, you will see exactly what happens to this when we use the fermionic variables. So hopefully it will be clearer then. And the second part of the question is, what is Grassmann physical meaning? Well, so the Grassmann variables physically mean that you are dealing with fermions. However, these Grassmann variables that we're introducing here, in order to replace the determinant with a Gaussian integration, they do not have any physical meaning whatsoever. Because, again, they were not present in your theory to begin with. This is just a trick to replace this determinant with something that's technically more manageable. Okay, there's another question. It's represented also as gauge field, as the same as gauge field. Well, if you're referring to the Grassmann variables, then no. I mean, the gauge field is completely independent. The Grassmann variables are completely auxiliary variables that we have introduced so far only to deal with the technicality, that we didn't want to deal with determinants. Rather, we want to deal with Gaussian integrations. So far, that's the only justification. Okay. Let's remember some basic formulas about adjoint representation of Lie algebras. So first of all, what is a representation of a Lie algebra? It's a homomorphism from the Lie algebra to, as I said, all matrices acting on some vector space V. And when I say homomorphism, what I really mean is that this map has to preserve the structure of the Lie algebra. And so what is the structure of a Lie algebra? The structure is that you can take any two elements of a Lie algebra. By the way, I'm writing Lie G every time instead of G, because one should write fractal G, and I cannot write fractal G. Okay, so the basic structure of Lie algebra is that given any two elements, there is something called the Lie bracket that gives you another element of the Lie algebra. And this Lie bracket has to satisfy the so-called Jacobi identity, which involves three elements, and this is an equation. Okay. So this is the structure of a Lie algebra. And this map has to preserve this structure. What that means is that suppose you take an element V from your vector space V, and then you act with the element X on V. So this action is given by, you take the representation of this element, which is a matrix, and then you act on this element V, which is a vector, simply by matrix multiplication. Okay. Now, if you take an element of the Lie algebra that is of the form X Lie bracket Y, and you act on V with this, this will of course, okay, so this has to map to the commutator. And to emphasize here this bracket means Lie bracket. Here, this bracket means matrix commutator. Okay. And matrix commutator will satisfy Jacobi identity. You don't have to worry about that. But this has to hold, right? So Lie bracket must get mapped to commutator. That means that this map, rho, preserves the structure of a Lie algebra and therefore is a representation of the Lie algebra. Okay. Now, there are many representations of any Lie algebra, infinitely many usually.
I'm sorry, can you just talk a little bit what the Jacobi identity physically means? What does that physically mean, if you have that relation?
Jacobi identity is infinitesimal version of associativity of Lie groups. So Lie algebras are the local version of a Lie group. So a Lie group, this relies a bit on differential geometry. So a Lie group is not just an algebraic structure, but it is also a manifold. And on a manifold, you can describe the local geometry by focusing on the tangent space at a point. And the Lie algebra is the tangent space at the identity element of the Lie group. Now, the Lie group, the group product of the Lie group has to be associated. And this imposes a constraint on the Lie bracket of the Lie algebra. Because again, so Lie bracket is an infinitesimal version of, I'm not sure what it's called in group term. Something. It's some structure like two group elements multiplied and then the inverse of that with a different order multiplied from another side. Now, in order to ensure that the group is associating, the Lie bracket must satisfy Jacobian. It's not a completely trivial proof. It involves some computations, but ultimately that's the constraint.
Okay, thank you. Thank you.
Yeah, no problem. Where was I? All right. So I was saying that for any Lie algebra, you will have usually infinitely many representations. But there's one particular representation that is very useful, which is called the adjoint representation. And you get this representation when you take as the vector space the Lie algebra itself. Okay. Adjoint representation. Of course, any Lie algebra is by definition a vector space. And when you choose as the vector space on which your Lie algebra acts, the Lie algebra itself, you get the adjoint representations. But what is the action precisely? The action is simply given by the Lie bracket. So take any element y from V. Again, recall V is the same as Lie algebra. And the action of x on y is nothing but the Lie bracket. Okay. So we said that here you take any vector from the vector space, and the action is given by some matrix. Here, it doesn't immediately look like that, right? The definition looks slightly different. You still have something from the same vector space, right? Because it's an element of the Lie algebra. But where is this matrix? So let's figure out that matrix. Actually, so before we figure out that matrix, is this true? Because we said that this has to be true for a map to be a representation. So let us introduce a notation. So let's say, let's call this thing add x acting on y. Okay. So we want to check whether this is true. So basically, another way of writing this is that for a map rho to be a representation, it has to satisfy the following. The representation of the Lie bracket of x and y has to be the commutator of the representations of x and y. Okay. Now let's check if that is true for the adjoint representations that we have defined. So let's start with this. Add x, y. Let's act on some arbitrary element. So we must show that this is equal to add x bracket add y acting on z. Okay. Let's check. So let's start from the left-hand side. Left-hand side. So by definition, this is xy bracket z, right? That's the definition. Add xy, x bracket y. This is this. Now we have the Jacobi identity. So let's use that. So if we use that, what we get is minus okay. Now we have to use the antisymmetry of the Lie bracket. Actually, maybe I forgot to say that there is a property of the Lie bracket. It has to be antisymmetric. Meaning the bracket of x and y is the minus of the bracket of y and x. Let's use that here. Here we want to do two things. Commute these two and commute this. So the sign will not change. Here we just changed the position of x. Okay, the reason that we did this is, let's look at this. So y commutator z is simply add y z. And then x, so now we have x commutator add yz, which again, using this, is simply add x of add y of z. Similarly, here you get add y of add x of z. Now, what is this? This is nothing but the right-hand side, right? Because you would break it down. So again, we said that this side is literally the commutator. So commutator means that add x composed with add y acting on z minus add y composed with add x acting on z, which is exactly this, right? Add yz, add yz, add x, and then reverse order. Okay, great. So what we have shown is that this map defines a representation. So meaning that this action where a Lie algebra element acts on another Lie algebra element by the Lie bracket defines a Lie algebra representation, which is called the adjoint representation. But now let's figure out the matrix form of this representation. For that, we need to choose a basis. Whenever you want to talk about some matrix acting on some vector space, you have to choose a basis for the vector space. And our choice for the basis is TA, where A goes from 1 to whatever the dimension of the Lie group is. The dimension of the Lie group is going to be the same as the dimension of the Lie algebra. Okay. It suffices to know the matrix form of the basis elements, right? So what happens if TA acts on TB? So we are computing add of TA on TB. This is TA commutator TB. And often you will see that, in fact, Lie algebra is defined by this commutator. And what people will write is something like this. Okay. Where these are reality depends on what algebra you have. But okay, there are some conventions whether you want to put an I here or not. And anyway, that's not super important. The main point is this is how a basis vector acts on another basis vector. But from here, you can figure out the matrix form of our adjoint representation. Right. So what was going on here previously? A vector is mapped to a matrix multiplying a vector. Let's copy this. Now, what is this in component? Vi gets mapped to row X, I, J, V, J. Now compare that with this formula. So what is happening here is that, so TA maps TB to I, F, A, B, C, T, C. So what is the matrix here? This is the matrix, right? So what you get from here is that add TA BC TC. I mean, this whole part is this. So add TA, BC is I, F, A, B, C. Okay. All right. So this is the matrix form. And this is the reason why I kept the dimension of the representation arbitrary. Didn't I write DMV at some point?
Yes, you did.
Yeah, now I forgot where. Okay, somewhere. Even if you're working with UN, right? So suppose our choice for the group G is UN, the group of unitary matrices of size n by n, right? Such that the Lie algebra of the same, which is small un, you will see definition of this Lie algebra as the n Lie algebra of n by n Hermitian matrices. Okay. But now notice that when this algebra acts on itself, it is not an n-dimensional representation, meaning that elements of this algebra are not represented by n matrices. What is the dimension of un? Okay, well, the dimension of this is, what is it? Is it n squared? N squared minus 1, maybe? Okay, so when the Lie algebra acts on itself, each of these indices, they go from 1 to n squared minus 1. So this matrix, this add TA, this is an n squared minus 1 by n squared minus 1 matrix, right? And it is acting on an n squared minus 1 dimensional vector space, which is un itself. So you just have to keep in mind that even if the algebra or the group that you are working with is defined as algebra of groups of matrices of certain size, not all of its representations are going to be of that size. You can represent the same algebra or the group structure using matrices of many different sizes. Okay? In particular, you can always define the adjoint representation, which has a different size than the size of the algebra. Okay. All right. I don't think we need anything more from here. The reason that we went through this is that we will see some representations, and when we discuss gauge fixing, we have to introduce some fields that transform under adjoint representations. That's why we looked at some of these formulas. Okay, now let's get back to gauge fixing in QFT, so infinite dimensional. But are there any questions?
Do you like pick and choose when you study up group theory and representation theory, or would you recommend like doing a whole lessons on those?
Oh, it depends on how much time you have. If you
Yeah.
if you want to be
Exactly.
efficient, if you want to be efficient, I would say, okay,
What
again,
would you
I cannot answer
recommend?
for everyone, right? Different
What would
people
you
have different
recommend?
interests. Again, it depends on what your objective is. If you want
My
to,
objective is to be a theoretical physicist, particle high energy theoretical.
sure, I'm okay. Even there are many variations. But if your main objective is to get into the advanced physics as quickly as possible,
Yeah.
you should just start reading physics. And then when you don't understand something, then go figure out what that is.
Okay. Got it.
But some
Okay.
people may be genuinely interested in the mathematics, and they may be interested in physics only as an application of mathematics. So then they should first study mathematics. So it depends on what you want to do.
No, physicist.
Sure, maybe you are, but I'm saying that some people may have other interests.
Yeah. Sorry.
No, it's okay. Okay, so now let's see what happens when we want to apply this to the infinite dimensional case. Right? First, let's try to visualize the gauge orbits, or we cannot really visualize the gauge orbits, but at least try to get some understanding of what we mean by them. In our finite dimensional examples, we said that we have two directions, x and y, and starting from any point in this space in this integration domain, there is a direction in which we can move without changing the value of the integrand, right? That was the idea. And these directions that we can move toward, starting from any point, these directions were basically the directions of the gauge orbits. So what is the analog here? So first of all, what is the integration domain that we're starting with in the QFT case? So we have integration over our fields. And just to be explicit, if you have like some field phi and then some fermion psi bar, also include those. Basically include all of the fields that you have. And then you have the gauge fields. Okay. So these are the integration domains, the space of all fields and including the gauge field. And so if you start from a point in your integration domain, meaning that you have chosen some fields phi. So I will not keep writing phi, psi bar. So whenever I write phi, imagine that I'm talking about all fields. Okay. Phi dot, and the gauge field. Now we have to find the directions in which we can move without changing the integrand. So here, our integrand did not depend on y. So when we varied y, we moved in the vertical directions. That was the direction of redundancy. So what can we do starting from here? We can do a gauge transformation. So starting from phi and a, you can construct another set of fields, phi prime dot a prime, which are given by gauge transformation, right? So phi prime is going to be rho of some gauge parameters. So here, maybe I should first write down the gauge transformations. Well, okay, I'm doing it here. So what are the parameters of gauge transformations? So you have one parameter for each basis vector of your Lie algebra, basically, because you have one transformation for each element of a Lie algebra, but you can expand each element of a Lie algebra in a basis. So it suffices to consider the basis vectors. So theta A acting on phi. And most importantly, these are functions of spacetime. Okay, so this is phi prime and whatever other representations you have. And then you have A prime. And A prime is minus covariant derivative of theta. This notation I have not, I think, written down before, so let's look at it a bit more carefully. Okay. So I wrote down the formula for transformation of A before. I cannot find anything I wrote down. What's going on? All right, I'm writing that again. Okay, A prime is A prime mu in particular is theta plus IG okay. And again, these are all functions of spacetime. Now recall that we have this formula that the adjoint action is the same as the structure constants, or basically the commutator of the basis vectors is the same as the basis vector accompanied by the structure constants. So whenever you see structure constants, this is basically coming from a commutator. So what's going on here is that this part is nothing but IG A mu acting on theta. And the eighth component of this thing. And just as a reminder, when I write A mu, that means it's an element of the Lie algebra. The components accompanied by basis vectors of the Lie algebra. Similarly for theta means this, an element of the Lie algebra. So there's a Lie bracket. After you check the Lie bracket, you have another element of the Lie algebra, and this is the component of that element. Okay. And this thing is nothing but the covariant derivative of theta, the eighth component, right? Because remember the definition of the covariant derivative was partial derivative minus I, Coxon constant, and the representation of A. And this representation depends on which field this covariant derivative is acting. According to whatever it is acting on, you will pick the representation associated with that thing. So here, the thing that the covariant derivative is acting on is theta. And we are saying that we're identifying this thing. I mean, this thing is nothing but the commutator. So what does it tell you about the representation associated with theta? I mean, we just discussed that the action of something on a Lie algebra element by the Lie bracket is the adjoint representation, right? And that is exactly what we have. So basically, this is nothing but Ig adjoint of A mu acting on theta. And then we take that component. Okay, so this is the covariant derivative for the adjoint representation. In other words, this theta is a Lie algebra valued object. And when this other Lie algebra valued object acts on another Lie algebra valued object, it acts via the adjoint representation. Okay. Right. So that's what I mean is going on here. So it's the covariant derivative in the adjoint representation acting on the parameters of gauge transformation. Okay, so what I was saying here is that you can start with any field configuration, which is a point in the domain of integration, like this point in here. And then you can vary it slightly. And you do this by doing a gauge transformation. And then the field configuration that you get is physically indistinguishable from this one, right? It's like moving, in this picture, it's like moving vertically up or down. Now here, you only had one parameter that you could vary. That was y. So there was only one direction that was redundant. But what's going on here? So how many directions do we have? In how many directions can I move starting from one point? So basically, we have a gauge transformation for any theta, right? So you have as many directions as you have parameters of gauge transformations. So how many parameters of gauge transformations do you have? So the question that we're asking is number of redundant directions. Here you only had one, right? You could, it was either plus y. I mean, you could, let's say, you could either vary y in a positive direction or negative direction. So plus minus doesn't give you any new direction. It's just opposite direction in the same axis. So we will not worry about plus minus, but disregarding plus minus, how many redundant directions do we have? So you have to count how many parameters you have. Okay. So each parameter is just a single number. Now, in order to get a single number out of this thing, you have to supply an explicit value for this index, and you have to supply an explicit value for this coordinate, right? And so this is where you have to recall our discussion about going from finite dimensional vector spaces to infinite dimensional function spaces. So this X is basically a continuum version of a vector index, right? So in total, the number of dimensions is basically the possible values of all the indices this thing has. So this thing can take dimension g values, but this thing can take infinitely many values. And the number of directions is this plus this. Okay, that's infinite. So in other words, the directions in the field space that are redundant are parameterized by these functions valued in the Lie algebra, and they're functions of spacetime. So for each of these directions, we have to introduce a delta function, and we have to compensate for the Jacobian, right? And that's how we will transition from our finite dimensional gauge fixed integral. I don't think I actually wrote down the full thing, but anyway. Well, this is a one-dimensional case. Okay, yeah, this is fine. So again, so recall that here we had one delta function for each redundant direction, and we had the Jacobian for all of these redundant directions combined. And we will now do the exactly same thing, just everything will be infinitely many. So here you will have one delta function for each value of the Lie algebra index and each point of your spacetime. And then you will have some complicated kind of determinant. Thankfully, we can convert that complicated kind of determinant into something less complicated. So that's what we're going to do. But before I move on, let's see if there are any questions. I'll check chat first. So one question. I can't help but notice that even though Bayesian integration is not actually integration in the usual sense, still when we do Gaussian integration using Grassmann variables, we get kind of similar results. Is there any deeper reason behind this similarity? You can answer it at the end of the session. Yeah, that's a good question. Well, first of all, I would say that even though the Bayesian integrations may look a bit different from ordinary integration, they are more similar than you may think. Well, it all boils down to how we define integration. I mean, if you only define integration how you may have seen it in a course on real analysis, then you're right. Then Bayesian integration doesn't look anything like that. On the other hand, you can define integration in a maybe slightly more abstract sense. Okay, I will not be able to do justice to this question. So I will just say that it is a bit curious that the results of the integrations are quite similar, and even the way that they are dissimilar is also interesting, right? In one case you get something, and the other case you just get the inverse of that thing. And honestly, I don't have a good intuitive explanation for that, other than that, okay, if I do the computation, this is what I find. But there may be some good explanation for why that happens. Yeah, I would say that you should try to do some research into why this happens. I don't really know. I think actually there was already an answer to this question. So what was it? So we can go beyond groups. No, is it maybe another question? We can go beyond groups for gauge theories. We can up the game 2 sets above and come up with monoids and maybe even semi-group gauge. We will start to lose physics from here, all mathematics like more. But was there an answer to this or no? Okay, I don't see an answer. Anyway, I don't have a lot to say about it, but the only comment that I may add is that there are physical interpretation of, say, two-group gauge theories. In ordinary gauge theories, you are basically studying holonomies of point particles. In two-group gauge theories, you are studying holonomies of strings. In higher cases, you are studying holonomies of higher dimensional membranes. It's basically the same idea with more indices. Okay. Right. Now let's try to translate what we have been doing for finite dimensional integrations to infinite dimensions. And keep in mind that this is what we're doing. For each value of this parameter, we need a delta function and some compensating Jacobian. Let's start converting finite dimensional notation to infinite dimensions. So I will copy the finite dimensional version first. Let's go component by component. First of all, what is going to happen to dmx? So dmx, so these are the variables that our function actually depends on. So these are going to be our fields. Okay, this is a bit tricky because we don't have a good separation of different kinds of fields. Okay, I will write something and then I'll add caveats. Okay, maybe have some fermions or whatever, and gauge fields. Now, again, as I'm saying repeatedly, this involves both of these things, the actual thing that we want to integrate over and the things we don't want to integrate over. So maybe I should say modulo gauge transformations. Okay. I mean, so this is not a mathematical formula, obviously. I am saying by word what I mean. That out of all of these integrations, pick something that's gauge, I mean, that where you're integrating over gauge non-equivalent things. This will be more interesting. So d and y means, in the finite dimensional case, this means integrating over these redundant directions. And now we have established that the redundant directions are parameterized by these variables, right? So roughly speaking, locally these will look something like integrations over theta. When I say theta, I mean all of the thetas, theta 1, theta 2, and the dimension of G. Okay, so combining this and this, we get just the integration over this field space. Let's copy this. Let's copy this. So we have this thing here, and we replace this with a fermionic Gaussian integration. And in order to do that, we had to introduce variables. Okay. So what does that translate to in the infinite dimensional case? So again, we have to introduce new variables. But how many variables we have to introduce? So recall that for each redundant direction, we have to introduce a pair of Grassmann variables CC bar. So now we have to do the same. So for each of this thing, we have to introduce a pair of fermionic variables, and we are going to keep the notation the same. So DC A, DC bar A. And just to highlight the fact that now there are functions of space-time. This is just a reminder that these are now functions of spacetimes. Previously, they were just Grassmann variables, but now they are Grassmann-valued fields of spacetime. Right? Because for each value of A and X, we need one fermions. So for each value of A and X, you need one Grassmann variable. Okay. Now, what about our gauge fixing functions? So we had f1 xy dot 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 fn xy. We have to find something. So again, for each direction, we had one function. So now, again, for each direction, we need one function. And these functions depend on the integration variables. Now, our integration variables are these fields, phi, psi, a, etc. So now we want functions that are valid in the Lie algebra because, just a reminder, we have these Lie algebra indices in our parameters. And they are going to be function of our fields, ax. Okay. So for each value of the Lie algebra index and each spacetime point, you have a function. And we will be more specific about this function. But of course, this function is not unique. You can choose whatever function you like as long as it satisfies some reasonability condition. But we will come back to that. But we also need to replace this operator. So here it is just a matrix, right? It's just an n by n matrix that acts on these vectors. So what is going on with that in the infinite dimensional case? What is this? Well, previously this matrix acted on these C's, right? So these C's were something like this. It was a column vector of Grassmann variables. Now we have these fields. So this matrix that acted on this thing should now be an operator. So whatever this is, it should be an operator that acts on CA, right? And previously, the action was that CI goes to del F, something like this. So now we want, let's say, I'm not carefully keeping track of upper and lower indices. But again, these are all raised and lowered with the delta from Kronecker delta, as long as we are in UN. So it should be fine. Now we want something like this, that this function should go to whatever operator we have. Right? And this operator can depend on x now, because this is a function of x. So even after multiplying by x, we will have some function of x. Okay. But in order to be able to explicitly write down an operator, of course, we need to know explicitly what f is. So let's try to come up with a simple expression for f. The first point is that there is no unique f. F is a matter of choice. But we can choose a simple one. A simple choice is given by fa, which is supposed to depend on all your fields and the gauge field. Of course, if you want to write down an f that actually depends on all of these fields, then first you have to specify a theory. You have to tell me what fields you have in your theory, and then you can write down an f. But the simplest choice is such that this does not depend on these at all. It only depends on the gauge field. Because in any gauge theory, of course, you have the gauge field, whatever else you have or may not have. So a very simple choice is this. Just take the divergence of your gauge field shifted by a completely arbitrary function, Lie algebra valued. Okay, so what are the properties of the same? It only depends on the gauge field. It is Lorentz invariant. And it also depends on arbitrary Lie algebra valued function omega a x. Okay. Why this? Well, it has to depend on something. And if it doesn't depend on any of the other fields, of course, it has to depend on the gauge field. Why Lorentz invariant? Because at the end of the day, we want to write down an action that is still Lorentz invariant. But this is not always true. In practice, sometimes you may want to break Lorentz invariant for sake of computation. Or maybe you are not trying to even model a Lorentz invariant theory. So then you wouldn't worry about this, and then there are other options. Why this? Because this is a completely technical point. It gives us a handle to do some manipulation later on. And of course, if you don't like it, you can always set it to 0. That's also a perfectly fine option. But for the moment, let's skip this. Now, since we have chosen an f, we should be able to explicitly compute this operator. So let's try to figure out what that is. So by definition, this operator is a derivative of the gauge fixing function f with respect to the redundant coordinates, right? And in our case, the redundant coordinates are the gauge parameters. Yeah, recall that starting from some any field configurations. If we vary the gauge parameter, so meaning that if the gauge parameters are 0, you have this gauge field configuration. But now if we change the gauge parameters, you have a different field configuration related by a gauge transformation. So delta gauge is a gauge transformation. So I turned on some non-zero values of the parameters theta. And then you have new field configuration. So you can, in this way, you can treat these gauge parameters as the coordinate in the directions of the gauge orbits, right? So we want to know the derivative of this function with respect to the gauge parameters. Now, how do we see the dependence of this function on the gauge parameters? Well, as I said, so these are the values of the function at 0 value of the gauge parameter. Now, we can do a variation by turning on non-zero values of the gauge parameter and see how this function behaves. So here, simply recall the Taylor expansion. So if f is any arbitrary function, and that depends on whatever variable you have, such as n. If you Taylor expand around 0, what that means is that you start with the value of the function when your parameter is 0. Then the next contribution is the derivative of the function with respect to that parameter, right? And then times that parameter. And then there are higher order corrections. But for a small variation, you wouldn't worry about higher order corrections. So let's mimic that. So we have f, which only depends on a, as we have established. So you simply have to replace a with a plus the gauge variation of a. And the gauge variation of a is the covariant derivative of theta. Okay. So if you evaluate this, I'm simply going to write down the answer. The answer is f of a, the thing that we originally had, and then an extra term. Okay. And this is just the covariant derivative, but written in a matrix notation. I mean, I think this is probably already clear to you, but what I mean here is that the first term is the partial derivative multiplied with Kronecker delta, and then you have Ig and the adjoint action of a mu, which is again a matrix acting on the Lie algebra itself. So it has a bunch of indices corresponding to the directions of the Lie algebra. So AB each goes from 1 to n squared minus 1. Anyway, so that's what I mean here. You could also just write it as covariant derivative of theta with the index a, evaluated at x. Okay. And of course, we don't need any higher order terms, right? We're only keeping linear terms. So now we compare with this formula. So in the second term, this term, z is the variation, right? The non-zero value of a parameter that we turned on. So it is simply theta, the non-zero parameters of my gauge transformation. So then what you have in front must correspond to this thing, right? We have to be a little careful because here we may have more than one index, in which case here we have a sum. Meaning that if you have multiple variables, then you have a derivative with respect to all of your variables, and then you have a sum over all the variables. And of course, here we have many, many parameters. So there must also be a sum here, right? And we have already seen many examples where a sum over discrete indices get turned into integrations. But where is the integration here? Well, so notice that we can write down this term as follows. Integration over a four-dimensional spacetime. Then a four-dimensional delta function. Okay. And here, by partial derivative, I mean partial derivative with respect to y. And also inside this covariant derivative, I have partial derivative with respect to y, and I also have the connection or the gauge field evaluated at y. So everything is y here. So this part only depends on the coordinate y. Or actually, sorry, should I say y? Well, it doesn't really matter because there's a delta function, but I think I should say x. X. Yeah, I should keep two things separated. Okay. Now, this delta function really simply collapses this y integration. So wherever you have y, you just plug in x. So now you have derivatives with respect to x, but this theta is a function of y. After the integration, this will be a function of x, and these derivatives will act on this thing. So this will simply give you this. The point of writing this way is that now you can explicitly see an integration. And this integration is the analog of a sum over this index I. So after this integration, whatever you have, which is this part, derivatives including the Kronecker delta, this really is the analog of this derivative. Okay. So what we established from this is that the derivative of f, and f as a function of x, by this I really mean f as a function of the connection evaluated at x. But this is a shorthand. Theta evaluated y. This is nothing but minus okay. All right. So after choosing a gauge fixing function f, we have figured out the derivative of f with respect to the redundant coordinates. And this happens to be this kind of operator. I think we have translated pretty much everything. Yeah, so we know what these things are. These are some new fermions. We know what this thing is. It's the operator. And the rest are the same, basically. I mean, you just replace these variables with this integration over the fields. Okay, so now let's put everything together and see what we have. So we have an integration over all the fields, integration over A. This whole thing is analogous to dx dA. Sorry, dx dy. Right. And then we had the determinant of the Jacobian, but we have replaced that with integration over dc bar. These are Lie algebra valid. I don't want to write the index because I don't want to give the impression that I'm only integrating over one component. I'm integrating over all of the components. So I could write the index and then take a product over A, but that's too much notation. So whenever I write dc, I mean integrate over all of the components of C. Okay. And then I have to translate these. So again, so here you have a sum over finite indices, which becomes integration over your spacetime. So here what you have is, so you had two summations, one over I, one over J. So now you will have two integrations. D4x, D4y, C bar, then this operator, this derivative. So there's a delta function, which we can use to kill off one of the integration, right? So I don't have to write the whole thing. So forget about y and write everything as a function of x. X derivatives with respect to x. And C. Okay. And this whole part is determinant of the Jacobian that we had. And then we have a bunch of delta functions. We haven't really said anything about what we are going to do with the delta functions. So for now, let me just keep the delta functions as they are. But you have to remember that there are actually infinitely many, one for each point over spacetime and for an Lie algebra index. So this is a very complicated delta function, but a delta function nonetheless. We will deal with it momentarily. And then the action that we had, which was what? I, S, phi, A, the Yang-Mills action. Okay, very well. So this is what we have now. It doesn't look too bad, except we don't really want to deal with this delta function as it is. We can get rid of it. And the way to do that is, it's rather simple. Let's recall what this is. Our f was divergence of A minus some random function. This, right? Okay. And we know from our previous argument that the final result of the integration is not going to depend on our choice of f, right? I mean, we proved this in the finite dimensional case, but let's assume that this continues to be true in the infinite dimensional case. So this whole integration does not depend on what we choose as f, because if we change f, this delta function will change, but also this determinant will change and they will compensate for each other. Okay. If it doesn't depend on f, that means in particular that it doesn't depend on our choice of this function omega. So whatever function we choose, the value of the integration is the same. So what we can do is that we can multiply this whole thing. We can multiply this whole thing by any function of this omega. And in particular, well, okay, I will write down the function later, but we can multiply these with, what should I write? So, okay, whatever function, so any function of omega. And then we can do an integration over omega, okay? Since the value of the integration doesn't depend on our choice of omega, this operation of multiplying by some arbitrary function of omega and then doing an integration of omega, this simply adds a multiplicative constant in front of the whole thing, right? You see what I mean? Suppose we have something that doesn't depend on some variable. Let's say variable w. It doesn't depend on w. Okay, so now you decide to multiply this by some function of w, and then you decide to integrate over w. So what you get is this thing times integration of the thing, right? And so you have simply multiplied your original thing by a number. That's what I mean. Okay. If we do that cleverly, so what I mean is that, so multiply by integration over omega and something that we can actually integrate. So a Gaussian function. This is a number, an arbitrary number, which we can control. So what happens if we do this? The integration is easy to do, right? Because we have delta functions. So omega will simply be equal to this thing. So the result of this integration is that you get rid of all of these delta functions, you get rid of all of these things, and you replace all of this by the square of this. Because all that you have done is that instead of omega A, you have plugged in the divergence of A. Okay. All right. So once we do this, now let's look at our final result. Now what we're left with is an integration over all of our fields.
Should that be 1 over or I over 2 psi?
Yeah, that's right. Maybe I missed an I somewhere. Here it looks like there should be an I, right?
Yep. Okay. Thanks.
Okay. Yeah, so integration over all of your fields, psi bar, if you have them, integration over your gauge fields, and then integration over these new fields that we added. And what are we integrating? We are integrating the exponent of your original action. So now let me break down the actions a bit as well. So let me first break down this part. It involves, I'm not going to worry about factors of half and etc. The kinetic term for your scalars, for the bosons, the kinetic term for your fermions, the potentials for all of your fields, the pre-existing fields. So this part is, after you do the integration over space-time, this is the action that you get by coupling your original theory to a background gauge field. Then you added the Yang-Mills term. This is Yang-Mills. And then we have this term. Notice that now this term is also in the exponent, so we can simply treat that as a modification to our original action. So what we have here is C bar, C, A. And lastly, we have this part which we created by getting rid of the delta function by doing an integration over this extra field that we had. And this really is the reason why we kept this field, so that we can get rid of this delta function. Because we already knew that the choice of f doesn't affect the integration, so we have this freedom to do the integration over omega. And here I will keep the coefficient because this is an arbitrary parameter. Well, why not keep the 2 as well? Okay. So this is our final action for gauge theory. Now let's try to, okay, these different parts have different names. So this part is called a ghost action. And these fields are called ghosts. Which is a very dramatic name, but all that means is that, I mean, the reason that they're called ghosts is that because they are physically meaningless, meaning that there should never be any observable involving these fields. So in a sense, they are invisible from the outside, hence the name. And this part is called, what's it called? I don't know if this has a name. It's just an artifact of our gauge fixing, right? Gauge fixing artifact. Okay. And remember that this parameter came from this arbitrary thing that we multiplied our action with and then integrated over omega. So none of the computations that we do should at the end of the day depend on this parameter. So if you compute some scattering amplitude and you find that your scattering amplitude depends on this parameter, well, you made some mistake. Okay. So basically, any action in a quantum field theory with a non-abelian gauge symmetry will look like this. So the only thing that will vary from theory to theory is which fields you had to begin with. So here I only had I wrote like one species of field, but maybe you have another kind of fermionic field, chi, which transforms in some other representation. Maybe you have more fermions. And maybe instead of one gauge field, you have two gauge fields. So then you would have another Yang-Mills term for the other gauge field. But all of them will structurally look almost like this. There are some possible modifications that are actually absent here. But yeah, we never talked about them. So, but this will be the main components of any gauge theory. So in other examples, so we discussed free field theory, and then we discussed interacting field theories without gauge fields. And you can recognize those terms in here, right? So for example, this kinetic term, if you break down the covariant derivatives, it starts with the kinetic term for a free scalar. Bunch of free scalars, but free scalar nonetheless. Here, if you break down this G mu, so the first term that involves only partial derivative, that's the ordinary kinetic term for a fermion, right? And then of course you are allowed to have whatever interaction you want, as long as it preserves the symmetries that you want. But then there are modifications because we added the gauge field. So what are the modifications? So let's look at some of the important terms. So here, for example, in here, if you break down the covariant derivatives, it does get a bit complicated, doesn't it? So for example, you would have things like phi dagger, partial derivative, and rho of mu acting on phi. You have a term like this. So this term comes from, in here you pick the partial derivative, and in here you pick the term with the gauge field. And this is an interaction term, right? It has phi, two copies of phi, and one gauge field. So in terms of Feynman diagrams, So remember that in the free field theory, we represented a propagator of phi by a straight line. So now we have phi, we have fermions, we have gauge field. So we have to introduce different notations for the propagators, right? So let's say that straight line is still correspond to phi. And remember how we construct interaction terms in the interacting theory. So what would this be? This be a cubic term, right? Because there are three fields. Two of them are phi. So you will have two straight lines. And then the other field is the gauge field. So let's assume that our notation for the propagator of the gauge field is a wavy line. So now this, you will have, in our Feynman diagrams, you will have vertices that will look like this. So two propagators of phi, and one propagator of the gauge field will come together to give a trivalent interaction. But here you also have other term. You can pick the gauge field from both of these derivatives, and that gives you a term that's phi dagger mu phi. You have to take them in the appropriate representations, but okay. This gives you a new kind of interaction term. You have two scalar propagators and two gauge propagators, right? And then you can have many, many different types of interaction terms here. For example, here you can have just a phi cube term, which we discussed. So it just looks like this. But here you can have, actually what other things you can have depends on the representations. But you can add, so I think you saw some examples of Euclid type interactions, which were basically psi dagger, phi psi type thing. But in order for this to make sense, the representations have of this thing have to be such that this whole thing can be made invariant. But assuming that it can do that, here you will have two fermionic propagator. Let's say these are dashed lines and one bosonic propagator. Then you have to introduce a propagator for these fields, right? Because this term, which is interesting because these are anti-commuting things, they are Grassmann variables. But this term, if you expand this covariant derivative, so the first term that you get from here is psi bar A, partial derivative psi A. This is the same kinetic term as you had for the phi, right? But the difference is that these psi things, they are Grassmann variables. This is a bit odd because when we had Grassmann variables before, we had fermions, and the kinetic term for the fermion, we argued that it has to be linear in derivatives because otherwise your Hamiltonian is not bounded from below. So what's going on here? Here we have fermions, but the kinetic term is quadratic. Well, as I said, that these things are really not physical. So in your Hilbert space, there should not be any state corresponding to excitations of these fields. And if you never excite these fields in your spectrum, you don't have to worry about boundedness coming from negative energy fermions, right? That's how we get away with these fermions having violating what is called a spin statistics theorem, which tells you that if you have bosons, they should have bosons should be commuting, which in turns gives you a quadratic kinetic term, and fermions should be anti-commuting with linear kinetic term. But it doesn't follow that theorem, but that's fine. They will not appear in our spectrum at all. But they do couple to your gauge field, right? Because from here, by expanding this D, you get term like C bar A, partial derivative A mu C A. And let's say that a red line is a propagator for your ghost field. So then this term is an interaction like this. Oh. Okay. So it's very similar to this interaction term. Well, not quite. It is a bit different because here you just had, no, it is pretty much the same. Yeah, but here you have ghosts. What else do you have? Okay. We haven't talked about the propagator for the gauge field. And you have to derive the propagator for the gauge field from these terms, right? These are the terms that involve only gauge field. So let's take a closer look at those things. Yeah, I think I am already slightly over time, but I'm also pretty much at the end, so it's fine. I will simply introduce a propagator for the gauge field. So let's look at the Lagrangian, the Yang-Mills Lagrangian plus the thing that we got from gauge fixing, this term, right? This term. So if you carefully expand all of the derivatives in these terms, so what you find is yeah, of course, I'm copying this from what I wrote down earlier. I mean, not here. I had it written down. Yeah, as you can see that it gets pretty long. And I'm no longer keeping track of upper and lower indices or Lie algebra indices. Okay, this is the full expression. Okay. Yeah, so this is what you get by expanding all the covariant derivatives in here and in here. Now, these are the terms that are quadratic in A. So these terms will tell you what the propagator for the gauge field is. And remember what the prescription for computing a propagator is in general. For any field, you have field, operator, field. This is the general pattern for the quadratic term. And when you have this, the propagator is always the inverse of the operator. Following that, here you get the propagator. So the propagator is the inverse of this stuff, including coefficients. So I will write down the equation for the propagator. And to avoid confusions, note that there are two G's. So the G without any indices, that's the coupling constant. And the G with two indices, that's the metric tensor. This is the quadratic operator that you get here. And the propagator, so now this operator has two indices. So your propagator will also have these two indices. And furthermore, your propagator will also have Lie algebra indices. I will explain why momentarily. Well, not explain, but just tell you. But the dependence on this Lie algebra indices is very simple. It's just a Kronecker delta. And as I said, that your propagator has to be the inverse of this operator. So if you multiply the propagator and the operator, you must get what is the analog of the identity, which is the delta function. So this is the equation that defines this propagator. And this equation is actually not that difficult to solve. The solution is as I was saying, the dependence on the Lie algebra index is very simple, just a Kronecker delta. It's the same term. Okay. So as we can see that this is really a Fourier transform of something. It's Fourier transform of this thing. So from there, you can guess that the easiest way to solve this equation is do a Fourier transform of both left-hand side and right-hand side. The Fourier transform of delta function is just 1. So then it becomes easy to solve. This is the solution. And then if we transform back to position space. And here, this is related to, so recall that at one point we discussed the how to make your path integration convergent. Because even though we are dealing with Gaussian integration, the thing that we have in the exponent is imaginary. And the way to make things convergent is to add a small real part to that exponent. And this epsilon is tied to that. The proper understanding of this must come from careful analysis of that path integration, but for now, let's just accept that if you do that carefully, you will end up with an I epsilon, where epsilon is a small number. And you will use this propagator with the epsilon in your computations, and at the end of the day, you will set epsilon to 0. Okay, so this is the propagator. So from here, you can guess that in Feynman diagram, when you draw a propagator for the gauge field, you have to specify these things as well. You have to specify mu and A on one side and mu and B on the other side. And then the value of this propagator will be given by this. Okay. So now you know the gauge propagator, but notice some other things that are new to non-abelian cases. So you probably have seen a lot of these things in the abelian gauge theory as well. But these terms are unique to non-abelian gauge theories because they involve structure constant, which are 0 in the abelian case. But these terms are simply interaction terms, right? Because they have multiple A's. So for example, from this term, you get an interaction term in your Feynman diagram that is trivalent in the gauge field. And from here, you get an interaction term that's quartic in the gauge field. Okay. So you have to precisely identify the values of these vertices, right? Because recall that associated to each edge and to each vertex in a Feynman diagram, you have some mathematical expression. So you have to read off this expression from here. So, and also, again, you have to specify some indices at each of the vertices. So here you have a mu. So for example, you have to specify a mu, b nu, and rho, c rho. And then there's a derivative. So we have to deal with that. The easiest way to deal with that is to convert this to momentum space, in which case this becomes multiplication by momentum. So in addition to telling me about these indices in the momentum space, these things must also come with a label for the momentum. Okay, so the rules are already quite complicated. I mean, not conceptually complicated, it's just a lot to keep track of. I mean, see how many type of interactions we have. So we have I haven't even written down all the interactions that you can have here. That depends on your choice of theory. And this. So in order to do any computation in this gauge theories, you have to write down all diagrams, all possible diagrams involving all of these vertices. As you can imagine, the number of diagrams grows very large very quickly. But anyway, at least in principle, we know how to do these computations. So I will stop here. Let's just summarize that all gauge theories in the world will look pretty much like this. Again, as I said, there are some terms that we have not discussed, some topological terms. But they're out of scope. But the rest will always look like this. So we'll have kinetic terms for your fields involving bosons and fermions. And because the kinetic terms now involve covariant derivatives, you will have these kind of interactions. And then what potential you have will depend on your choice of theory. Different theories will have different potentials. So this potential is the place where you specify which theory you're talking about, what physical phenomena you're trying to model. All of that goes in here. And this part is pretty much universal. Yang-Mills term, kinetic term for the ghosts, and this gauge fixing term. Okay. So now you know how to write down the action for any gauge theory, and also in principle how to do Feynman diagram computations. Of course, in order to really understand these things, you have to do some computations. Hopefully, some of those things will be in your assignments at some point. And so this concludes the theoretical construction of gauge theories. Now that you know how to construct a gauge theory, or what the component of a gauge theory are, you can now study different phenomena involving gauge theories. Some very interesting things that unfortunately we did not have time to talk about are, for example, symmetry breaking. And one reason that we really did not try to talk much about it is that this really becomes most interesting when paired with renormalization. This term you may have heard many, many times. So just to give you an idea as of what this is that we already briefly mentioned that here, when we talk about field propagating, we have to specify their momentum. And depending on, if you can put upper limit on the momentum in a Feynman diagram. So you may not want to allow fields of energy higher than some limit to propagate. And if you do that, then depending on the upper limit, the coupling constants of your theory may change. Obviously, I have not explained the mechanism of why that will happen, but it can happen. And depending on the value of the coupling constant, many, many interesting things can happen. You may think that, okay, if you continuously vary the coupling constant, things will continuously vary. But that's not always the case. For example, so coupling constant is a parameter of a theory, right? So similar to, let's say that you were trying to write down a model to describe the states of matter, let's say water. So then the parameter of a theory will be like pressure, volume, temperature, etc., etc. Now you can continuously vary these parameters, and most of the times things will vary continuously. That is correct. But sometimes if you go from one phase of water to another phase of water, right? So keeping, say, pressure and volume fixed, you lower the temperature too much. Suddenly you go from liquid water to solid water, right? So now things are changing drastically. So in a liquid water, you would have certain kind of correlation, right? Correlation would probably decay very fast because water is liquid, so wave will not propagate as nicely as they will in solids, for example. So if maybe you are computing correlation functions in liquid water, and then suddenly you lower the temperature too much, and then the correlation will jump dramatically. So that kind of things will happen. And those things are tied to symmetry breaking. Obviously, the symmetries of water and symmetries of ice crystal are very different. And what else? So, okay, once you have understood renormalization, some other things that are closely tied to that are asymptotic freedom. So this is the idea that in a non-abelian gauge theory, if you allow very high energy, this really applies to the standard model. So if you allow very high energy, or in other words, you are looking at things from a very close range, so then the quarks, which are some fermions, like this size, they will appear as free, almost non-interacting. But if you look at it from far away, they will appear to be very strongly coupled. So strongly coupled that you will never see two quarks separately. Yeah, that kind of things. Again, yeah, these are very interesting things. But unfortunately, we didn't get to discuss much about them. Hopefully, now you have enough material to study some of these things on your own, or you can take a more advanced QFT course. But first, I believe that you have some upcoming lectures on more phenomenology-oriented topics. So I believe you will see some of these things actually in practice. So hopefully you will get to practice some of your theoretical knowledge in more practical contexts. Okay, so I will stop now, and if you have any question, I will try to answer. Thank you for attending.
In this, thank you. In this generalized expression for a non-abelian case, you have the Grassmann fields. Those are for the Jacobian, right?
You mean these ones?
Yeah, yes.
These are for the Jacobians, yes.
Okay.
Okay, well, okay, sorry, there's a bit of a delay, but maybe you can see now. So these C's are for the Jacobians, but the psi's are not for the Jacobians. They are fermionic fields that we already had in your theory.
Okay. Okay. All right. Thanks. Thanks.
You're welcome.
So if there aren't any other questions, should I stop recording?